Well, pleasure to be here and talking about some fun stuff that we all are excited about with the new release of Java 8. Java 8 has brought to the world the almost every reasonable mainstream programming language now supports a functional style of programming. So I think it's a very exciting time to be in programming all over again. So we want to talk a little bit about functional style of programming. So the first question I would start out with, why care? I mean, we've been doing programming for a very long time. What's really exciting about functional programming? And I want to kind of outline, first of all, things. When we write code, what we're doing is we really are communicating. We're communicating with fellow human beings who are as passionate about programming as we are, but really need to develop applications that are maintainable. So one of the really important things about functional programming, in my opinion, is it really gives an opportunity for us to be very highly expressive and convey the intent very quickly. Like, let's look at one example here. Let's say I want to just find out something extremely simple, common, we're used to. I want to know if some numbers are primes. So I'm going to say is prime, and let's just say a few numbers we know about, 1, 2, and then maybe 3 and 4. And I want to know if these are prime numbers. So how are we normally used to writing this? We would normally start out by saying, given a number, we would say, well, the number is prime if it's not divisible by any number between 2 and 1 less than the number. In other words, it's only divisible by 1 and the number itself. So normally what we end up doing is we would start with an iteration off the bat. And then we would say something along the lines of, let's iterate through the number, and starting with the 2, of course. And then we would say, well, if we find out while we iterate through this that the number actually is divisible by the index, we would then say this is not, we would then say return that the number actually we are looking at is greater than 1, because by definition 1 is not a prime number. So here is an imperative style of programming, and we can see the result is false, true, true, and false. So that seems to have done the job fairly well. We could write more tests around it. But the point is, what did we just do here? We started by focusing on the iteration. I think that's where the problem is in us trying to write code. We end up focusing on the infrastructure. We end up focusing on the implementation rather than keeping the focus on the essence of what we're trying to do, high ceremony. So we could do this in a much more effective way by focusing on the problem rather than the looping. So we could, for example, say, first of all, return that the number we have on our hand is greater than 1, first of all, right? If it's not greater than 1, it's not prime. And then we could say, well, why don't we just say integer stream, which is part of Java 8, and then we will get a range of numbers. So range from number 2 to number -1, that's a closed range. And then we can use, none matches the given an index value off the bat. We could say that the number given to us is not divisible by the index. So what we did here is we took the focus away from the looping, and the code begins to read more like the problem statement. So is it a prime number? Well, it's a prime if it's greater than 1, and if none matches in this range of numbers, that we don't have divisibility in this range. So that's one of the biggest essence of functional programming, is that it's declarative rather than being imperative. We don't end up telling it not only what to do, but how to do it, but we focus on just saying what to do and let the code deal with how to do it. The difference may be small syntactically, but it's enormous semantically, because now we have the option of deciding how these operations are performed. Now, if you really fundamentally think about it, if you take any collection of values and send it to a for loop, that is pretty static. The for does exactly what we tell it to do, in this case, sequential looping. But we have polymorphism on our hand when we use functions like range and none match, because we're not telling how to do it, we're just telling it what to do. This could be done sequentially. If you want to convert this into parallel, maybe because the numbers is a very large number, we don't want to compute them sequentially, turning this code into a parallel loop is enormously simple compared to the sequential approach and the imperative style of code that we are used to writing. So that's kind of where we are with the functional style of programming. So what does that mean to us from the point of view of programming? It allows us to be more highly expressive. We are able to focus on the essence rather than the ceremony. So there are two things I would say about imperative style of programming. And one is saying how, right? And the other smell is mutability. So we all know that mutability is evil, but yet we have done that quite often. Now, what's wrong with mutability? The minute we have mutability in our code, we have to make sure we don't change it inappropriately. We have too many moving parts in our code. Right here is an example. We focused on iteration. This is a very familiar code, but complex, because we got to start the I value at 2, and then we have to make sure that the value is incremented properly. We got to send the bounds properly. So we are focused on too many moving parts here. And the more moving parts we have in code, the more errors are in the code as well. So mutability often leads to more bugs. Not only that, with mutability, it's hard to make the code concurrent as well. So in the case of declarative style of programming, we focus more on, in the case of declarative, we focus more on not how, but what we want to do. And we avoid mutability, we favor immutability. And these two are really powerful. We can write declarative code outside of functional style, but functional style is declarative. So that is the benefit, is we do more declarative programming when we do functional style of programming. And that is enormously beneficial, I think. So given all of this, where do we go from here? Java 8 has introduced some really phenomenal capabilities. And by essence, we can start utilizing some of the most powerful capabilities, the expressiveness, as I mentioned about that. So let's think about this problem we just talked about. Let's actually continue a little further on this. If you look at the is prime, we already made it concise, but I think we can go a little bit step further with this. And this is where some of the real fun in programming comes about. We want to make the code expressive. Look at this for a minute. That's something we're going to stare at for a second and say, huh, what's that doing? And to me, if we spend any time staring at a piece of code, we have not communicated properly. I want the code to read like a story, not like a puzzle. We don't want to sit there and scratch our head wondering what the code is doing. So notice what we could do here. We could say, for example, let's say we have a method that we are writing, and the method is going to be another Boolean, and I'm going to say is divisible, right? So we could say is divisible. And we could create code, and that becomes expressive. So we can pass some numbers to the is divisible and say, can you find out if something is divisible by this particular value? But in this case, we want to be able to capture this number because that is the essence we have to pass here. But we can do some really interesting things with expressiveness in code, because all we are passing to non-match is a predicate. It's going to tell us whether this code is matching this criteria or not. So with lambda expressions, we have things like lexical scoping, enormously powerful. It allows us to capture a state. So we could say, for example, create a predicate here, and it's going to take an integer, and I'm going to say is divisible. And what I want to pass to this is a number, a divisor, if you will. And then I could simply say return number that we have on our hand is divisible by the divisor equal to 0. Now, if you look at just this code that we have on our hand, of course, we're going to have the integer in this case. We don't have to specify integer type inference will kick in. Great. Now, if you look at just this part over here for a second, we clearly know what the divisor is. That's a parameter coming in to this anonymous function lambda expression. But what in the world is this number? Well, this reaches out to the defining context and captures it. That's where the lexical scoping comes in. And with the lexical scoping given to us, now we can simply replace this code with simply, let's start in the beginning. We can say, given the index, we're going to simply say is divisible by, and then we could pass the index given to it. And then we can say, go ahead and execute that particular function that I have into that context and execute it. So we can start to write more expressive code along the way, and that really favors a much better style of programming, as we don't have to stare at the code and wonder what's really going on. let's look at a couple of examples of this. Let's say we are interested in a small problem. The other thing about imperative style is, like I said, it turns into a puzzle, then a story, and we begin to wonder. So let's take a little problem. Find the double, let's say, of the first even number greater than, let's say, 3. Well, that's a very simple problem. Find the double of the first even number greater than 3. But how would I write this as imperative style? Well, we would first of all say result equal to 0, and then maybe I want to output the result once I find it. And then we would start with the collection given to us. Let's say the collection given to us is, let's say values equals, and then let's say arrays dot as list, and let's just presume these values to be the values we want to start with, and let's say we want to go through these values. I'll make just a small change here to make this a little bit more interesting. So in this case, we got a bunch of values on our hand, and what I would like to do is I want to find out if these the result. So what would I do? I would iterate through, and of course you don't want to go through the traditional iteration that's so old. We could simply say int an element in values, and what we would do here is we would simply say if the element is greater than 3, first of all, and if the element is divisible by 2, we would then say, well, I want to go ahead and say result equals element times 2. Well, but that's not enough. We have to break out of this loop. So notice again, we are focused heavily on the mechanics of the looping at this point, and that's where our effort is given. The result is 8. Why is the result 8? Well, the first even number greater than 3 is 4, and 4 times 2 is 8. Well, but unfortunately, something is wrong in this code, and we don't even know what it is at this time, until maybe a tester comes back one day and says, well, your code sucks. And we say, yeah, I know my code sucks, but tell me how it sucks today. Well, the problem in this case is, what if well, actually, I won't even answer that. Let's go ahead and do this in functional style, using declarative style, and see if the problem reveals itself. So I'm going to say values.stream. So what is a stream? A stream is a fancy iterator given in Java 8. And I'm going to say, given the stream, I'm going to go ahead and ask the stream to perform a filter operation. And the operation I want to perform here is, given an element, whatever element that's given to me, tell me that element is greater than 3. Then I ask him to filter one more time, and this time I say, given an element again, tell me if the element is even, and then finally we say, go ahead and find out for me a double of all the values. Given an element, give me the double of all the values that are even and greater than 3. Then we finally say, find the first value for me from this collection, and then get it for me, right? So what we did here is we used a very highly expressive declarative style of programming. And we simply said, given these values, we simply want to be able to go through and find this particular value we are looking for. What happens if we run this? Well, if I run this example, I did get the value 8, but if I remove this get for a second, stop a step earlier and try to run it, it tells us something pretty intriguing here. It said, I won't give you a result, I'll give you an optional 8. And maybe we immediately say, aha, of course, because it's possible that the given set of values may not have any even number at all, or may not have any number greater than 3 at all. It may be an empty collection, who knows? So notice how that problem is hidden in the imperative style. We have to think through it, whereas that reveals itself very easily in a more of a declarative style. That is one of the things I really like about functional style of programming. But we can go a step further from this to make it more expressive. For example, I can take this part of the code, it is taking is greater than, and I can simply say over here, let's say static Boolean, and I don't mean to say that all methods are static, but in this particular example, given the context of the example, so I can say is greater than 3, for example. I could say number, and then we could simply say over here, well, just return if the number is greater than 3, right? So we could say number is greater than 3. But what's the benefit of this? The benefit is we can now come to this code and say the sample class is greater than 3. So now the code begins to become more expressive with this wonderful thing called the method references available in Java 8. So similarly, we could go away, this could go away, and we could simply say sample is even, for example, where the is even could be a method we are implementing within this class. And so we can say, for example, here, static again, Boolean, and we could say is even. Again, given a number on my hand, I want to simply return if the number that I'm given is actually an even number. So mod 2 again equal to 0. So we can begin to become more expressive in the code, and now we can start reading the code. What are we doing? Given a set of values, filter out all the numbers greater than 3, then filter out all the even numbers, and then double them. We can again put a method reference for it, and then find me the first one. So we can see how this becomes more and more expressive, and the code begins to read like the problem statement. So that's kind of what is exciting to me. What's your thought?
So, Venkat, can you hear me okay?
Yes, absolutely.
Yeah. Okay, that's great, and I think that one of the questions that many people have, there is actually one question, Paul, that which I can ask you in a second. But one of the questions that many people have, you mentioned that you move towards a more declarative approach of writing code, which is fantastic, because it's more about saying your intentions as opposed to implementing your intentions. And in the imperative approach, it's more about showing how to do it. The other benefit you were talking about, it was in terms of concurrency and being able to, having immutability, etc., avoiding those types of for loops, etc. But under the covers, a question is, under the covers, this is ultimately implemented in a specific way. It's using those for loops, etc. So is one to assume that the library is taking care of all those little details?
Well, that's a very important question to think about, and a couple of things we need to keep in mind, right? Ultimately, everything goes down to machine code, but we don't want to be writing in machine code. Certainly, we are working on higher levels of abstraction, and almost every language we program in is Turing complete. So, but that doesn't mean that there are no consequences. The differences are enormous, because when you are dealing with a filter and a map, this is not the traditional for loop that we are used to, because there is quite a bit of optimization that goes on in some of these implementations. For example, one of the biggest trends we have on our hand here is, notice we didn't send a result, instead we provide a function to this function. So this brings up, in functional programming, we use what are called higher order functions. So what that means is, we can pass a function to a function, which means that this function can either decide to evaluate this function now, or it can evaluate it later, or may not even evaluate it at all. So in other words, this leads to a powerful lazy evaluation. If I really think about functional style of programming, we talked about how does it feel to write the code, and we said it's declarative, it's expressive, it is something that we can just easily communicate. But let's turn the question around and say, what other benefit do we derive from it? And to me, there are two main gems of functional programming, looking at it from that point of view. And one is lazy, and the other is composition. We already saw the composition here. Notice how this flows through, and that becomes very expressive. We go through a transformation of objects rather than mutation of objects. But on the other hand, the lazy evaluation to me is probably one of the most powerful things. This opens door for so many possibilities. If we write a traditional for loop, even internally, for loops are normally eager evaluation. They evaluate right away, and to really make them lazy takes a lot more effort. But the filter on this hand is actually lazy. Let's see actually how that is true in just 1 second with this example we just started out with. So to understand how that works, let's convert this just a little bit more, and we will say here sample, and we'll call it as double it. And this is a really small example, pardon me, but the one that actually brings out the essence really well in my opinion. So let's say we have a double it, which takes a number and as an argument, and I'm going to simply return here, let's say number times 2. Well, the result is great, it produces, but imagine we wrote this as a traditional for loop, eagerly evaluating the result. What would we do? Notice we have 10 different input, which means we're going to find if every one of them is greater than 3, so that's 10 operations, keep that in mind. Then we're going to see if anything greater than 3 is going to be even, and that would be 7 more values to be evaluated right there. So 10 plus 7 is 17 operations. Doubling all the even numbers, that's 4, 6, 8, and 10. That's 4 more. So we got 21 operations to perform. That seems like a lot of looping to do if we were doing this in a traditional for loop under each one of them. But thankfully, that's not the case. So if you notice here, I'm going to output here is greater than, and I'm going to simply say here called for, let's say 3, and then we're going to say a number that we used to call here. So similarly here, I'm going to output, let's say is even, and then I'm going to specify number again, so we can actually see this being called. And then finally, I'm going to output double it, and then see if double it is being called here on the number. And notice the surprise from the output we see now. Well, it started out, first of all, in the output, it asked if 1 is greater than 3, and then 2, and then 3. But then notice, after 3, it went to 5. And once it examined 5, it said, oh, look, 5 is actually greater than 3. I am going to go ahead and apply is even operation on that value. Well, 5 is not even. Forget that then. Then when it goes to 4 and starts over with is greater than for 4, does even for 4, doubles 4, hands it off to the find first, and the find first says, oh, I'm so happy, thank you, that's all I needed, and everything shuts down after that and goes home. It doesn't evaluate the rest of the values at all. So what we're seeing here is the effective laziness we just got for free by using the stream. And so if this was purely a mapping over to traditional for loops under the hood, we're not going to get these kinds of benefits. So what Lambda expressions do here, the fact that these are functional and declarative, the expressiveness opens door for some beautiful optimization. And so what Java 8 did here is it fused these operations into one operation. And in Java 8, methods like filter and map are really called as intermediate operations, and methods like find first, reduce, and collect are called as terminal operations. So these operations don't even execute while you are passing through. And if I were to grab all of this into a single variable here for a minute, let's go ahead and put this here into one variable and save it here as just let's call it as temp over here for a minute. And if I evaluate this temp further and ask for a temp.findFirst over here and get the value, well, the result is going to be exactly the same as we did before, but for a minute, just remove this final phase from here and run the code, and notice the quietness that you're going to see now. Because all these were lazy, and they never really did any work until the terminal operation triggered its evaluation and says, now can you go do minimum work for me? And that is one optimization that this style opens door and shows that it's not a direct mapping over to the traditional for loop under the covers.
Yeah, that's absolutely very valuable to know, I think, and the emphasis there is that you're getting all of this for free as a side effect.
The beauty of, if we write the code well, there is so much improvement it can be made to it. But if the code is shabby and mutability all over, the compiler looks at this code and says, I don't want to touch this stinking code with the 9-foot pole, and it leaves it poorly optimized. But when the code is, it's kind of like what we would do, right? If I write a report really bad and give it to you to review, you're going to find all the grammar errors in it. But if I write it and spell check it, make a good grammar, revise it a few times, maybe give it to a friend and look at it, then I give it to you, now you're going to talk about, hey, let's look at the content you have, look at how you can improve this, you can talk about this, you can talk about that, and we are going beyond these trivial checks, let's find the bug here, bug there, into really good optimization. So it feels like we're giving a better quality code to the compiler, and the compiler pats us on our back and rewards us with, hey, here's some optimizations I can do for you for free. So better quality code results in better optimization, and that is the lesson I've learned looking at this, I think.
Yeah. There's a couple of questions, Venkat, if you wouldn't mind,
Please.
quickly answer. because it's in the context of what you're showing. There's one question from Dennis that says, is the optional type parameter still erased at runtime in Java 8?
The type erasure is still the problem. So I really don't want to talk about generics, because the minute somebody mentions generics, I get so angry. I still am bitter about generics type erasures. But the hope is that there's an option, maybe eventually in the future we'll have good reification and that would get resolved. But yes, unfortunately, the type erasures still do kick in.
Okay. There's another one that says, can you replace is greater than and is even with lambda expressions, which I think that originally it was, right?
Yes, so yeah, absolutely. So you can go back and forth with this. You can say, I don't want to have a method reference. I would rather, have given a value. I would rather say e is greater than 3. You can certainly do that. In fact, what you can do here is you can even say, given the value e, I want to say e is greater than the value e, and you can pass it down the chain like this if you wanted to, and you can see that the result is still the same. But the beauty is the IDE now kind of nudges you a little bit and says, hey, do you really want to keep that way, or do you want to replace this with method reference? And then you can say, yeah, I want to opt out for that, and then you can kind of opt in and opt out. Method references are really charming, but I have one advice about method references. I'm a huge fan of this slogan, and my slogan is make it work first and make it better real soon. As we are getting used to Java 8, method references can be very intimidating. And my recommendation is, don't fall into the pressure of making the code concise, because what you may think as concise may actually be terse to somebody else reading it. So go ahead and write the code with lambda expressions, get comfortable with it, and then if absolutely makes sense that a method reference can be used instead of a lambda, then go ahead and change it. But give time to get comfortable with it. And if you use nice IDEs like what we have here, they can even prompt you to say, hey, this is a good candidate for use for method references. But one of the rules of method references is, if you look at this code right here for a second, notice we receive the parameter and we simply pass the parameter to this function. Imagine for a minute we had to do a ×2, for example. Well, if you do something like that, did you notice the IDE doesn't prompt me to go use method reference anymore, because it figured out that there's actually a bit of intelligence in this code, so method reference cannot be used here. But if it's a simple pass-through where what you receive is what you send, and I was thinking about this, and I gave this a pattern name for this when I was writing the book, and I called this the office space pattern. Remember the Office Space movie? In that we have Tom, and what do you do, Tom? Well, I take the requirements from the business people and give it to the programmers. So this is like the Office Space pattern. There's no intelligence at all happening, and those are the cases, good candidates for conversion to method references, because there's no intelligence going on in the code. But we shouldn't be eager to run towards them. We should evolve the code and get comfortable before we use them. So absolutely, there's nothing wrong with using lambda expressions instead of method references until we get comfortable with it.
Okay, that's great. Right. So I think in terms of questions, let me just check. There is one which says, great, but can we use it with the date? I'm not sure if what do you mean
with the date, as in the new date API, or can we use today?
I'll follow up with that.
Okay, well, let me actually answer both of those questions. The date API, absolutely. That also gives quite a bit of fluency. We can use it. Well, we can use it today as in, so I've got a couple of suggestions for that. I was teaching a course on Java 8 recently, and one of the gentlemen said, hey, we are beginning to use Java 8, but we are releasing libraries that are used by people still on Java 1.5, 1.6, 1.7. So what gives? What can we do? Well, the beauty is, when you start designing your libraries for use with Java 8, use SAMs, or single abstract method interfaces. And when you start using single abstract method interfaces, those using Java 7 or earlier can still send anonymous inner classes to the code, and those using Java 8 can send lambda expressions, and depending on how they compile, the compiler will essentially determine whether to use invoke dynamic under the hood or to use the regular anonymous inner classes. So your library that uses single abstract method becomes quite viable, easy to use in different versions of Java, and it's very easy to see this interoperability really strong. So absolutely, we can start designing API today, even if we are programming in Java 7 or 6, but start designing with single abstract method interfaces. So when we do adapt Java 8, the transition becomes simpler. And then also, if you use IDEs, which are really good at recognizing these smells, they would look at your code and say, hey, look, this code can be easily converted to a lambda expression, and then as you start using Java 8 on the projects, it can do conversions for you and reduce the amount of code as well. So absolutely, there's a lot of power to us to think about how we can design with that.
Okay. Thomas, that previously asked the question about can we replace greater than and is even with lambda expression. He clears it up by saying that what he actually meant is whether you can assign the lambda expression to a variable, what type is greater than.
Got you. So if I have an E, and that's a wonderful thing to think about. There are not too many times that you would want to do, but let me say one reason why you definitely want to do. I'm a huge fan of good design, and one of the things we should absolutely avoid at any cost is duplication of code. So imagine if we're going to have this lambda expression E greater than 3, and for whatever reason, let's say we have to use it again, maybe down below in another expression, and we're going to use that in another expression below. Now we have duplicated that logic, and that is pure evil to duplicate code like that. So what we want to do to avoid that is we would say, well, first of all, what does a filter really take? Well, a filter takes a predicate. It's very easy to see that. You can look at the filter and say, oh, filter takes a predicate. I understand what that's taking. And what's a predicate? A predicate is a SAM, a single abstract method interface, and predicate itself has a test method. So if you look at predicate itself, you will notice it simply has a method called test. So that gives a context to what we are dealing with. So in a sense, a filter is just accepting a predicate. So what we can do here is we can simply say, give me a predicate which takes an integer, and I can say is greater than 3. In fact, I highly recommend this, and the reason I recommend it is you don't want to write static methods and pollute your class for the logic you need. Instead, it's nice to create a function within a function itself using the lambdas. So here I'm going to say, given a number, I want to return if the number is greater than 3, and now I can simply replace this with the suite is greater than 3 and ask him to do the work. So of course you probably want to give the good name here is greater than, so greater than 3, and you can do something along these lines, and then you can say it. But look at the beauty of this. You can do this, sure, but you can go even a step further. What if you really wanted is greater than 4 later on and greater than 5 later on? You don't want to duplicate this code. Duplication is fundamentally evil, and we should eliminate it as much as we can within reasons, of course. But what can we do? Well, here's an idea. Rather than doing this, let's go ahead and create a function for a minute. This function takes an integer, but it returns a predicate of an integer. No, that's a little bit intense to begin with, but once you get a hang of it, you would love it. So is greater than, and what does this do? This is a function, and this function says, give me a pivot, for example, and what I'm going to return to you is a number, given me a number, the number is greater than the pivot. So if you look at this code, what we just did here is we created a function called is greater than, which takes a pivot value, but returns a predicate that tells me if the given number at that time is greater than the given pivot. Again, lambda expressions can capture the context in this lexical scoping. So now I can simply say is greater than, and then I can pass a 3 to this function right here as an apply call. So apply is a function of function, and so we can say is greater than apply 3. So this is a eager evaluation. that returns a predicate that we saw here, and that predicate, which is really this one that we are returning with a 3. But later on, if we don't want a 3 and use a 4, we completely reuse this piece of code rather than duplicating it. So this is the beauty of this. I really like the question that was asked, because this shows us how we can end up removing duplication in code and have these as little building blocks. But let's take this one other step, if you will. You can now wrap this into a utility class, and rather than utility classes giving you functions that return results, your utility classes now can have functions that give you functions. So that's the difference between giving somebody a fish and giving somebody a fishing lesson. You generate functions that can be used over and over on the receiving end, rather than giving a function that will only return a result when called upon. And this gives a lot of ability to customize and generalize code much more effectively. So this is a very exciting way to think about it, in my opinion.
So this is actually this leads to another question, because you talk about composition of functions, right? Here what we're doing is basically we have, now in your case we have a main function, and inside that main function we're composing it of another function, and then inside there's a filter which is taken as greater than. When it comes to, I mean, traditional models of object orientation, where you have, for example, a class, and you have this you know, a typical class that talks to a database, and then we've learned about dependency injection and how we can pass in the dependencies and change the behavior during the test, etc. How do we approach that in this functional way? How would
that's a fantastic question. And yeah, it's a fantastic question, and I think the reason why it's fantastic is it really hits the nerve of the possibility here. In a great way, we have injected dependency injection right here in the code to filter. Because what we are telling is, we're telling the filter, hey, your job is to filter the values in this collection, but I am going to give you the details of filtering in a lazy manner later on. And so if you really think about it, what is dependency injection fundamentally? Step by step backward for a minute and look at what does it mean, dependency injection. It is nothing but a very glamorous way of thinking about the strategy pattern, right? Because we are saying, I've got different variations of strategies. I want to write a code in a general way so that I can inject the strategy as dependency during the code execution time. This is exactly what we are doing. So dependency injection is essentially a strategy pattern. You don't have to use dependency injection only in object-oriented programming. In a sense, this is extremely powerful, because if you really think about it, let's go to a bit of a simpler example to think about how the dependency injection plays a role in a slightly different context. Let's say for a minute we're going to write a function to take these values and total them. So we could say, for example, over here, int total values. And then we're going to give a list of integers, let's say numbers over here. We'll call it numbers. And all I want to do is just total these values out. So we could say, for example, numbers. Let's take a traditional imperative style. We can convert this to a declarative style in a minute. So I'm going to return the result over here. But we could say for int element in numbers. And we could then say, given all these number values, I want to simply total the result. So result is plus equal to the element. But rather than totaling all the values, if I really wanted to total, let's say, only a select values, what are the select values? I don't know. I can decide that later. I want to be able to vary that. So what we normally do is we would create an interface here. Maybe we'll call it as a selector, and we will say the selector is going to be passed in. And what would we do as a selector? Well, in Java, we are used to creating an interface called a selector interface. And then we would specify in this interface a public, let's say Boolean, let's say pick, and then we would say integer value. And we would then leave out and say, hey, that's an interface, we will implement it later. Then we would say class even selector, and then this would be implementing the selector. This is called ceremony, and we have been led to this in OO programming quite a bit, isn't it? And then here we would say if the value is even, so we would say mod equal to 2, 0, then accept it. But all this is a fluff, because we are forcing ourselves to implement objects. But what are we really interested? The essential part, right, is this part right here. What is all of this? This is called the ceremony. Ceremony is what we have to do before we get to do what we really want to do. And we have entertained ourselves with all the ceremony so we could get to this fun part of writing that expressive code. Let's see how we're going to do this now. Let's keep the selector for a minute. Let's not throw that out. Let's keep the selector for a minute. So I've created a selector, and I'm going to come here and say if the selectors is going to have a pick method. If it picks the element, then I want to add the result, not otherwise. So we still did what we did in OO programming. We still what we did in Java. We haven't done anything very differently. However, when we come to call it, we say, given an element, simply return a true for me, please, because I want to total all the values. So in other words, rather than creating a class, we end up focusing on the essence, which is the function we want to perform. So right there is a dependency injection, because to me a dependency injection is nothing but a strategy pattern, and that's what we are applying here. So this selector became a strategy, but of course we don't have to go through that much effort because this is already baked in. We can turn this into a predicate, for example, and then we can say that takes an integer, and then now we can say, well, that's going to be just a test function. We can run through that now, and now similarly we can say total values and then give the values and say, given an element, tell me element is even, and we can say only total even numbers and not anything else. And now quickly we can say, all right, now that we are performing those two operations, well, let's actually output the values just to see it here. And we can see in this case, now that we have the result of this, let's make this E is going to be even. And we can turn that around to more of a declarative style very easily by simply saying, why all this fluff again? Simply say that I want to take the numbers given to me, well, return numbers again. And given these numbers, I want to simply say, get me the stream. And from the stream, I want to filter out only the values that I want to select, and we can just send the selector to it. And then we can say, reduce these values, starting with the value of 0, and I want to perform a sum, so we can simply say map dot, exact, add exact, and ask it to perform that operation on it, and we can see that the result is still 55 and 30, so we can again make the code very expressive, but that became your dependency injection. So depending on what you're doing, you're still passing an object, so you're still doing exactly what you did in Java, except on the calling side, we don't have the ceremony of a class. We can. Nothing stops us from creating an anonymous in a class and sending it, or refer to an existing class with this method, but this becomes a lot lightweight. We're able to focus on the function rather than the class that we have to build. So the beauty here is we get this benefit of mixing object composition along with function composition as well. So this is a mixture of the two that we can enjoy rather than being restricted to one or the other. And I think that is the benefit moving forward.
That's great. We've got quite a few questions piled up, but before moving on to the attendee questions, there are two other questions that we wanted to discuss. Is there, apart from the lazy evaluation that you've spoken about, is there any more to streams that we should know? For example, parallel support, etc.
So one of the biggest benefits of streams itself is, streams is like this magic that happens with the enormous amount of beauty and power to us. So for example, let's take a very trivial example here. Let's say I have a list of values that I want to start with, and this could be anything we do depending on the computation we perform, and let's say equal to a list of numbers we have on our hand, and given these values, let's say I want to double each of the values and total them. Now this could be stock prices coming in, this could be other values we deal with, who knows what these values are. And I'm going to say over here, well, how do I go about totaling these values, a double of these values? Well, we could say numbers.stream, and then we could say, for example, we could perform a map operation. Map is a transformation. So given an element, we would say, let's go ahead and say sample double it, and I want to double the values, and then when I'm done with it, I'm going to actually, in this case, say map to int, because then I can simply use the sum operation on it to perform the double operation. So we can see this. Now, what is this double it that I'm going to use here as a method reference? Well, let's go ahead and say this is going to be a method which is, let's make this a static method as well. It's going to give us a double it value, right? So double it. And this takes a number and returns, let's say, number times 2. So return number times 2. But just this is a hypothetical example. Imagine for some reason this is a very slow operation. So I could say, for example, thread.sleep, and maybe this has to go to a web service, get some data, do whatever that it has to do to perform this operation. And so I'm going through this and working through. Imagine if we had written this sequentially using a for loop. I won't write the loop here, but we would have said for int element e, and then we would have written the for loop. So we could have written it using a traditional style as well to perform this operation. So if I go back and run this little example that is going to double the values and sum it, we can see that it's taking some time to run. And how much time it's going to take? Well, a little bit more than a 6 seconds delay, and gives us the result. So you can see the delay in there. That was about a 6-second delay. But the beauty is we performed a functional hygiene. If you look at this method sample, it is pure function. What is a pure function? A pure function is a function that has no side effects. It takes an input and it gives an output. So one benefit of a pure function is it's easier to test it, because as long as we keep sending exactly the same input over and over and over, it gives the same output all the time. So writing test on it is very trivial compared to writing a test where mutability is happening in the code. So the point really is, this is a pure function. Well, when we have a pure function, we have what is called referential transparency. So what is referential transparency? Referential transparency is where the compiler can replace the method with the result of the method if the input is going to be the same. So if you call double it and send me a 4, no matter how many times you call double it with a 4, the result is going to be always an 8. So I could replace a double it parentheses 4 after a first call with the value 8 and no longer have to incur the overhead of calling it. Not only that, when we have referential transparency, we can rearrange the code quite optimally for performance reasons. But one benefit of that is the stream can say, hey, look, when I'm evaluating this, I'm sequentially evaluating these values one by one by one, and that's taking really long time. 6 seconds is eternity for a lot of us, and it gave the result. But let's just simply say parallel stream rather than a stream, and we just kind of put it in a turbo mode with one flip of a switch. And notice this time the result came back in about a second rather than 6 seconds. So if this was a very large collection, now here's where I get really annoyed when people talk about performance without context. If performance is really important, let's revisit that for a second. If the number of input is really small, you don't gain great performance one over the other. It's generally a wash. If your input size is very, very large, your real performance gain doesn't come from running the sequential code a little faster. It is like going to somebody who's bicycling and saying, bicycle faster, pedal faster, pedal faster. If you really want to go to a different place within a matter of magnitudes of speed, you don't ask somebody to pedal faster. You go get an airplane or a rocket or a car, depending on the distance you are traveling. In a similar way, if I have a very large collection and I really need good performance, what I really need to do is to opt to multi-threading. Well, the problem with multi-threading is the minute we take the for loop, the traditional for loop, and we touch it to make it multi-threaded, the code no longer looks like the code we once wrote. It has turned into a monster. And so what does concurrency mean? People start messing with the code, try to fix the bugs they introduced, and they update their resume right away and concurrently apply for another job because the code has become a monster. Well, that should not be what concurrency is. So the point really is we should be able to go from a sequential code to a concurrent code in cases where we can without expending so much effort. Notice that's taking about 6 seconds to run, but because we maintain functional hygiene, the stream says not only can I run in lazy mode, I can also run parallel if you just want me to. So we still control the switch, but it goes into a turbo mode when we flip the switch, And that opens the door for that kind of optimization very easily because of the declarative nature, because of immutability being honored. And I think that's a very powerful tool on our hands as programmers.
That's awesome. And how is this like, because, for the past years, I mean, Eric Meyer, who we all love, used to work for Microsoft, and he came up, he worked on the reactive extensions, and now that's become part of the Java space. RX Java, Netflix has been doing that. So how does this all fit in with reactive programming? I mean, is there any, like, does one replace the other? Is there, do you use them together? How is it related?
That's a wonderful question, and what's really exciting is, when I looked at reactive programming, it is as if like looking at this like, of course, was the reaction when I looked at reactive programming. So take what we did so far here. We addressed two very important capabilities here. One is the expressiveness, and the other is the lazy evaluation. And the third, of course, if I went off by one error, and the third one here is, of course, the ability to parallelize these things. But there's a couple of problems on our hand when you look at parallelization. Well, laziness is awesome, great. Parallelization is awesome, that's great. But what's going to happen if for some reason the function you are calling here were to throw an exception? Let's say you are going to a web service and asking for some data from the web service, and that data doesn't exist. And it's going to give you an error, and you want to propagate that as an exception. If you're doing this sequentially, you can handle the exception right away. But if you're doing this concurrently, multiple threads are running, one of them bombed, how do you know things actually failed? So take reactive programming as a higher level of abstraction. Reactive programming takes bits and pieces that's available in front of it and raises the level of abstraction. The first one is lazy evaluation. You want a client and a server parts working with each other, but you are really producing results and the consumer is consuming it, but you only produce results as and when the consumer wants it. So think of this as an observer pattern with a few things added to it. The lazy evaluation, ability to communicate back when a termination happens from the server side, ability for the client to tell the server, thank you but no thanks, don't evaluate anymore. So since you are evaluating lazily, you can evaluate only on demand. As a result, you're not eagerly evaluating and wasting resources. And all this gets added up. So think of reactive programming as ability to do lazy evaluation, ability to communicate, a good observer between client and server about interaction terminations, and also lazy evaluation. Add on top of it the resilience part, where when one of the components end up failing, that exception is propagated through a very clear abstraction, so the receiver can actually handle the error and then can say, now that I got this error, I no longer want to do anything more, or ignore this error, I've handled this on my side, let's pretend that we have more work to do, please give me more data. That kind of abstraction can happen. So reactive programming is, you could say, functional programming plus, where you are taking the lazy evaluation, the parallel streams. And so to go back to your question, how would you build this? When I program in reactive applications, I use streams, I use the laziness of stream, but under the hood, inside of the reactive API. So the reactive API gives me the abstraction to provide the observer mechanism, but on the server side, I use the stream for providing that laziness of evaluation, and then reactive API tells me whether to evaluate the next element or give up and say this is done, or communicate back to the client to say I'm done with my processing, go do something else or tell me what else to do. So that is higher built on top of functional programming. You cannot imagine doing reactive programming without the capabilities that functional programming has offered, like the laziness, the purity, the referential transparency. All those wonderful things add up together to provide reactiveness. So this is a perfect storm where all of these coming together to a higher level of abstraction. Very exciting way to look at it, I think.
Yeah. So we have got about 4 more minutes, Venkat, and there's a ton of questions. I'm going to try and go through some of the important ones, or those that repeat, and then we can see if we could follow up with some of the other ones later on. Sure. One of the questions is, there are questions here in terms of, what are the benefits of me using Java 8 if I'm already using Scala, for instance? And I don't think that we could really get into these types of questions with the few minutes we have left. I don't know if later on you want to maybe follow up with that. But there is a question of, should I be using Java 8 right now for new projects in production?
So let me quickly address both of those. The answer to the second question is yes, you should. And the reason is the sooner we start using it, the sooner we begin the experience for it. And it's been around for a long time. People have tested it. I've seen the interaction on the mailing list. So absolutely go ahead using it. And to quickly say the Scala versus Java is it's not one versus the other. Now that we have this available in all the languages, interoperability becomes really easy. Scala will benefit because of invoke dynamic as well, and we can interoperate a lot more. So if you're already using Scala, that's great. There's nothing wrong with it. Continue to use it. But if you're going to have to integrate with Java code, you can also benefit this on the Java side as well. And of course, you can begin to start using a better interoperability between the languages. So I don't think it is as a one versus the other. We can benefit from learning from both options and see which one is better and pick the one that makes sense.
Okay, and I think with just the last question is it possible to use currying or partial function applications with Java 8?
So currying is something that's very easy to build for ourselves. So for example, really quickly, you can say, I want to take a lambda expression, like let's say we wrote a predicate, so we could say predicate.curry, and then what does curry really mean? So what you can do is you can write yourself a little curry function, right? So your curry function will say some input, let's say integer value, and then within this, what you can do is you can say return, you are going to return some function, let's say function, and whatever function you want to return, which takes two parameters, for example, you simply say, in this case, I'm going to take one parameter, give a result, but the other parameter I intended to take is the value coming from here, so you would use that value within your expression. So in other words, currying is nothing but a nice little use of lexical scoping to capture one value so that you can use that value in creation of another function. Partially applied functions are a lot more difficult because the language would have to support that fundamentally, and Java 8 doesn't do that, but currying is not hard at all.
That's great, Venkat. I think we're out of time, so let me just switch over a second.
Yes.
So first of all, before I continue, I want to thank you very, very much, Venkat, for this awesome webinar. It was really great. I really enjoyed it, and I think that we had a very high attendance, and I think people in general have very much enjoyed it. Unfortunately, we haven't had time to get to all of the questions, so we'll see what we can do about that later on. So thanks again once, Venkat, for taking part in this. Appreciate it.
Thank you.
For more information from us, for feedback in terms of if you want to get in touch with Venkat, please email venkat@agiledeveloper.com or on his Twitter handle &venkat_s. In terms of us, for more information about upcoming blogs or webinars or features of some of the things of Java 8 that we support in IntelliJ, please visit our JetBrains.com/idea website, as well as the blog and the JetBrains TV, where we'll be publishing, including this webinar. And if you want to learn more, please follow us on JetBrains and IntelliJ. And Venkat, once again, thank you so much, and thank you everyone for taking part. And we will be publishing the recording very soon, and see you next time. So thanks again.